We're going to go ahead and get started this morning. This is going to be the first of 2 weeks, because it's going to take us at least 2 weeks, hopefully not more, where we're going to be talking about matter. First of all, thank you guys for coming back. It's always nice to see returning faces and nice to know that I'm not scaring people off. Before we get into the argument, I want to ask us some preliminary questions this morning to get us thinking. You are new. I'm sorry. If you're lost, watch the videos. There's QR codes over there.
I don't have any capacity to be lost. It's fine.
There you go. It's okay. I want to ask us some preliminary questions this morning to get us started thinking about this. Some of them are going to be easy questions that hopefully everybody can answer. Some of them are going to be rhetorical questions that I don't expect an answer yet. First question, does matter exist? This is one of the easy ones.
It matters.
Matter exists, right? Matter obviously exists. How did matter get here?
It was made.
It was made? Maybe, maybe not. Let's think about this systematically. I want to present an either-or scenario. Either, at one point, matter didn't exist, and then it popped into existence, and now there's matter. Or matter has always existed. There's no third option there. Either it's always existed, or if at some point it didn't exist, it popped into existence, because now matter does exist. Okay? Can it have popped into existence? And while we're thinking about that, what scientific laws might apply to that scenario? The next question would be, can it have always existed? And what scientific laws might be applying to that scenario? And then given what we see in any of those scenarios, the answers to any of those questions, does what we see line up to our naturalistic, atheistic assumption? Now, somebody that has been here, what does that mean when I say the naturalistic, atheistic assumption?
The belief that there is no God.
The belief that there is no God, and the belief that the material universe is the only thing that exists. Okay, and in this class, we're assuming that that is true. What happens under that assumption if we find a scientific law that breaks?
It breaks the entire argument.
It breaks the entire argument. It all falls apart. Because if you are a naturalistic atheist, and there's nothing more than the observable material universe, then the laws of nature that bind the material universe should always apply. They can never break. So if ever we find a situation where a natural law breaks, naturalistic atheism can't be true. Okay? So as we go through and look at these arguments, let's think about, do we see the law break? And if we see any laws break, what does that mean about the naturalistic atheistic assumption? Okay? Can matter spontaneously generate? Can it just pop into existence? What do y'all think? No. Of course it can't, right? Normal everyday life will tell us that. But what does science have to say? Anybody know what the first law of thermodynamics states? Go for it.
Matter can either be created or destroyed. Not matter, energy can either be created or destroyed.
Energy can neither be created nor destroyed, but it only changes forms. That's actually word for word, exactly. You've got this. It's like you've heard this before. Right out the gate, it does say energy. You corrected yourself from matter to energy. That's good. From a scientific perspective, energy and matter are kind of interchangeable, because energy can be converted into matter and matter into energy. We see this, say, with photosynthesis, with plants. They take sunlight, they make food. We see this. We're going to get into an example. When you burn something, it takes the physical matter and it makes heat and it makes light. Okay, you can take the matter and turn it into energy. The two are kind of interchangeable. This first law of thermodynamics applies to everything in the observable universe. Okay, so what this is saying is that the energy and matter levels in the universe have to be constant and have to have remained so throughout all of the history of time. In any given closed system, the amount of input and output must always be equal, even if matter has turned into energy or vice versa. So when plants take sunlight and make food out of it, there's no more or less matter or energy in the universe. There's the same amount, regardless of whether it's in matter form or energy form. Okay, the same amount exists, it's just in different forms. So I want us to think about the whole universe as a system, as a closed system. And we'll get back to what that closed system is next week. But just bear in mind, we're thinking about the universe as a closed system. The amount of inputs into the universe and the amount of outputs from the universe have to be the same. Okay? It's kind of difficult for us to wrap our head around the output of the universe because the universe is still actively existing. It's not like the universe is concluded and we can observe the outputs. But they have to be the same throughout the entire process. So with wherever we're at in the timeline of the universe, the amount of matter and energy that we have has to have been the same throughout the entirety of the history of it at the beginning, and will continue to be the same until the universe ends. If at one point no matter existed, but now matter does exist, this law has fundamentally been broken. So again, our either or. Either at one point matter didn't exist and it popped into existence and now we have matter, or matter has always existed. That first option can't be true. Otherwise this law would have been broken. And if atheists want to think that this law has been broken, then they can't be atheists. So under the naturalistic atheist assumption, the first option can't be true. Matter has to have always existed. Then we come to the second question, can matter possibly have always existed? Anybody know what the second law of thermodynamics states? Go for it.
Can I close system entropy?
Essentially, yeah, that's the brunt of the argument. We're going to get granular with the amount of definition. It says in any change, the universe becomes a slightly more disorderly place. The entropy goes up, the information content goes down. This is really clunky wording, and it is so because the laws of thermodynamics are foundational to basically everything in science. They can be applied to engineering, to astromechanics, to all sorts of different avenues of scientific discovery. So the foundational laws, first and second laws of thermodynamics, have to be generic. What this means, the information content goes down and the entropy goes up. The amount of usable energy and matter is decreasing. Matter and energy are constantly deteriorating into a less and less useful form. Every time that one is converted into the other, every time that matter interacts with matter and energy interacts with energy, they're constantly becoming less usable. The usable energy supply is deteriorating. The usable matter supply is deteriorating. So, given a starting point, if existence were to go on forever, matter and energy would eventually completely deplete themselves. Okay? Now let's use the timeline. That's the first time we're actually using the timeline in this class. This is going to be exciting. Let's pick a point on the timeline. Let's just start here. Eventually, because we're here, but eventually, let's call it the wall, let's call it in Harbor Freight's parking lot. I don't care how long it takes. Eventually, if you start somewhere and you keep going down the timeline, matter and energy will just cease to exist. Okay? The issue then is if matter has always existed, if there's an infinite historical timeline, then matter and energy would have already depleted themselves. So let's define, like say, start here and say it takes 50 yards worth of timeline for matter and energy to deplete themselves. Given an infinite historical timeline, we can go however far that way we want to go. We can go 50 yards that way, we can go 100 miles that way. So if matter has always existed under an infinite historical timeline, then by the time we get to where we're at, matter's already depleted itself. So we come to this paradox where if matter has always existed, then matter wouldn't exist. That's a lot. Does that make sense? Everybody with me? Ish. Sort of.
So the answer is no.
The answer is no. Yeah, matter could not have always existed because if it did, it's a self-defeating argument. It would have already ceased to exist. Matter can't spontaneously generate because of the first law of thermodynamics, and it can't be eternal because of the second law of thermodynamics. So under our naturalistic atheistic assumption, if both of those scientific laws held true, should matter exist? No, it's our either-or scenario. Either it popped into existence or it's always existed, and neither can be true. Semi-trick question, does matter exist? Yeah. We've already established that, right? Matter shouldn't exist, but matter does exist. Okay, and this is proof, not necessarily of God, not necessarily that the God of the Bible created everything, but it's proof that both atheism and naturalism are wrong. They're fundamentally incorrect assumptions. But they don't like that. The naturalistic atheists don't like that. They want to explain it away. So now we're going to come to the part of the show where the atheists come out and say some silly things. And we're going to explore various atheist challenges to this idea that matter shouldn't exist based upon the scientific laws. And we're going to see whether or not they hold any scientific water. This is evolutionary physicist Victor Stenger, and he's writing in his book, God, the Failed Hypothesis. And he said, where does energy come from? The first law of thermodynamics requires that energy must come from somewhere. In principle, the creation model could be confirmed by the direct observation or theoretical requirements that the law was violated 13.7 billion years ago at the start of the Big Bang. Essentially, God exists. The God of the Bible has to exist. The Bible has to be true, scientifically and objectively, if the laws of thermodynamics held true at the beginning. But they don't want to accept that. They don't want the God of the Bible to exist. They don't want the creation model to be confirmed. So they're going to come up with all sorts of outlandish ideas, all sorts of crazy theories to try and explain away how the laws of thermodynamics didn't apply, or at least didn't apply in the way that we've thought about them applying. The first one being quantum mechanics. Don't get too scared yet. We're not going to get into the nitty-gritty of quantum mechanics. We're just going to look at a quantum mechanical theory. Why are my AirPods connected? I'll never know. They're not your AirPods. This is true. Earlier we stated that matter and energy can be converted into each other. And this is a process known in quantum mechanics as a quantum fluctuation. So in 1973, a physicist by the name of Edward Tryon, it's a hard name to pronounce, he proposed a theory that the whole universe is just a massive quantum fluctuation. Essentially, at the beginning, all matter was just quantum fluctuated into energy, and then there was just a massive quantum fluctuation back into matter. So it looks like to us, matter popped into existence, but in reality it was just all energy. It gives the illusion that matter pops into existence, but that's not actually what happened. Surely there's no problems with this, right? Surely there's no scientific problem. There's a couple of problems. The first one being that there is a major difference between speculation and actual scientific observation. Okay, one of them is scientific, the other is silly. The mass conversion of all matter into energy or all energy into matter has never once been observed to occur. Not even close. And many quantum physicists question whether such fluctuations are even possible. This is MIT particle physicist Robert Jaffe, and he said that there is a flippant way that people refer to the evidence for real vacuum fluctuations, but there is no evidence that the vacuum fluctuations exist in the absence of matter. Essentially, if the theory is true, and all matter was just energy, there's no evidence to suggest that there could ever be a fluctuation of energy back into matter. There's no evidence to suggest that this theory is even possible. This is a quote from a science writer by the name of Ralph Essling. Hard names to pronounce this morning. He says that all things begin with speculation, science not excluded, but if no empirical evidence is eventually forthcoming, or can be forthcoming, all speculation is barren. There is no evidence, so far, that the entire universe, observable and unobservable, emerged from a state of absolute nothingness. And it's really important here that he mentions that evidence is eventually forthcoming or can be forthcoming, because there's no evidence that the vacuum fluctuations exist in the absence of matter. And there can never be, because we will never be able to observe an absence of matter. If ever there's a situation where all energy is converted into matter, we cease to exist, because part of us is energy. If ever there's a situation where all matter is converted into energy, we cease to exist, because part of us is matter. We will never observe this. We will never be able to find evidence. And because we will never be able to even think about finding evidence, then this kind of speculation is barren. This theory is not founded in the science. The other problem is actually a sleight of hand, and they're redefining what nothing is. Okay, their argument is that all matter could have been converted into energy, and that the entirely energy quantum vacuum would count as nothing. But if everything was simply in energy form, That would be a quantum vacuum. That would not be nothing. Scientifically speaking, nothing is kind of tricky to define and even harder to pull off. So let's look at a couple of quotes here of what scientifically would count as nothing. This is editor-in-chief of the Scientific American, Philip Yam. And he said that energy in the vacuum is very much real. According to modern physics, a vacuum isn't just a pocket of nothingness. It churns with unseen activity, even at absolute zero, which is the temperature defined as the point at which all molecular motion ceases. So even if all molecular motion has ceased, the vacuum is still moving. The vacuum is still doing stuff. There's absolutely something there, even if it's not matter. This is mathematician Martin Gardner, and he said that it is fashionable now to conjecture that the Big Bang was caused by a random quantum fluctuation in a vacuum devoid of space and time, but, of course, such a vacuum is a far cry from nothing. This is physicist Richard Morris, and simply put, he says, in modern physics, there is no such thing as nothing. This is a subatomic physicist by the name of Richard Webb, and he said that according to quantum field theory, even if there was no quantum vacuum filling it, empty space would be anything but nothing. And this one's fascinating, because so far we've been talking about all matter being converted into energy and it appearing as if there's nothing. He's saying that even if that energy didn't exist and there was actually nothing, it still wouldn't be nothing. This is theoretical physicist Alexander Verlinkten, and he said a more fundamental problem is that Tryon's theory, this is the guy that started this whole quantum fluctuation thing, his scenario does not really explain the origin of the universe. The quantum fluctuation of the vacuum assumes that there was a vacuum of some pre-existing space. And we know that a vacuum is very different from nothing. Vacuum, or empty space, has energy and tension. It can bend and warp, so it is unquestionably something. Quantum mechanics never produces something out of nothing. The idea of a fluctuation implies that there is something there to fluctuate in the first place. So if all matter simply fluctuated to energy, our reasonable next question would be, where did all the energy come from? It still couldn't have come from nothing. Nothing didn't really ever exist. That's a fun sentence to figure out what the negatives mean. Nothing never really existed. So where did the energy come from? Remember, our problem that we posed to the first law, between the first and second law of thermodynamics, is about matter and energy existing at all. Okay, they've simply moved the problem from matter to energy. They still have the same problem. If all matter was fluctuated into energy and it just looks to us like it was spontaneous generation of matter, fine, where'd the energy come from? It's still the same problem. They've just moved the goalposts. Does that make sense? Any questions, comments, anything? Cool. Now we get to talk about the zero energy balance. This one is so dumb. Anybody know who that guy is? Look at that, Stephen Hawking. He's not very well known in the scientific world. And he proposed this theory. This is his answer to the scenario. He said the answer is that the total energy balance of the universe is exactly zero. The matter in the universe is made out of positive energy. However, the matter is all attracting to itself by gravity. Thus, in a sense, the gravitational field has negative energy. In the case of a universe that is approximately uniform in space, one can show that this negative gravitational energy exactly cancels the positive energy represented by matter, so the total energy of the universe is zero. And so here's why his theory kind of would work mathematically. First of all, we've already talked about this a little bit in this class. There is a proof that we're not probably going to actually get to. We're just going to assume that the proof is true. If you want to see the proof, I'll take 15 minutes after class. I can show you the proof. But it shows that if matter exists, then time has to exist. And if time exists, it's because matter exists. The two are linked. You can't have one without the other. And they're linked by gravity. If gravity exists, it's because matter exists, vice versa. So if there's always matter and gravity in existence at the same time in the same proportions, which is true, theoretically this makes sense. And the math behind this makes it make even more sense. The energy balance can be described by that equation, where x is just some variable, m is matter, g is gravity, and b is the balance of the energy. And what Hawking proposes is that matter and gravity are always equal, and that the balance is equal to 0. So if, at the beginning, there was no matter and you subtract no gravity, then the energy balance is 0. And if you add 100 matter and you add 100 gravity, the balance is still equal to 0. Does this get around our problems with the laws of thermodynamics? No. Not even close. There are several problems with this theory. And the first one is actually a two-parter, because Hawking makes two major assumptions in his theory that are unverified and completely unverifiable. The first one being that the universe must be approximately uniform in space. This has been shown to be demonstrably false. The portion of the universe that we have observed is not uniform at all. Okay, it's clumpy with clusters of stars and galaxies rather than being evenly spread out in space. This is cosmologist and Stanford professor of physics, Andre Lindy, and he said that newfound voids have upended the prevailing view of the universe as a smooth, uniform mosaic. The cosmos, we have learned, is akin to Swiss cheese or foam, with galaxies clumping by the hundreds of thousands across colossal cavities. And we can see this here. We've got galaxies, clustered stars in galaxies across massive empty space. It's not uniform. It's not even close to uniform. This is science writer Adam Hadhazian. He said that the universe incorporates important deviation from, I'm not going to try to pronounce that word, homogeneity? Sure. Namely, stars, galaxies, and other agglomerations or clumps of matter. It's not uniform, let alone approximately uniform. It's not even close. The only way that they can potentially argue that the universe is even close to uniform is at extremely macro scales. If you zoom all the way out on the universe, it might look somewhat spread out evenly. It might look somewhat uniform. But it's basically impossible for us to evaluate anything at that large of a scale since we've simply not observed all of the universe. And, logically speaking, given that it's not true at the smaller scales, it's probably not true even at the larger scales. Okay? So to presume, just to make your theory work, just to make your worldview hold together, to presume that it is true is not only an illogical leap, but it's not supported by the available evidence. And by definition, that assumption would be unscientific. Assumption number 2 is that he claims that the negative energy must exactly equal the positive energy. This is fundamental to his theory. And this claim is simply unverifiable. We have not observed all of the universe, again, like we've said before. So there is no way that we could possibly know anything about the total energy of the universe. Whether it's positive or whether it's negative, we can't know. Let alone about the sum of the energy of the universe. This is astrophysicist and cosmologist Tamara Davis. And she says that trying to tally up the energy of the universe is a futile exercise. The total energy of the universe is simply undefinable. These two assumptions are fundamental to Hawking's theory. If either one of them aren't true, his whole theory is out of the water. Okay? But they're completely unverifiable. Especially this one, because we can't even define the energy of the universe, let alone sum it up. So much for following the evidence where it leads. But wait, there's more. Hawking just completely makes up this idea of negative energy. Out of nowhere. Like, negative energy is not a thing. He says that, in a sense, gravity is negative energy. But strictly from a physics perspective, there's no such thing as positive or negative energy. Energy is simply energy. It just is. We may think of energy as negative from our human perspective, but that's only from our perspective. As humans, we exist in the material realm, so gravity is constantly pulling at us, right? Because we exist in the material realm, by definition, gravity would be pulling at us. So gravity seems negative to us, but in reality, energy, even energies that are in opposition to one another, are not positive and negative energies. They're just energy. They just are. The fact, as Hawking claims, that gravity is negative energy is, again, fundamental to his idea. But it's simply not what the evidence indicates. That's not how energy works in physics. Even more problems. The problem presented to atheists that we've presented by the laws of thermodynamics is not the signs of the energy, it's not the sum of the energy, it's not the value of the energy, it's the problem that energy exists at all. So this solution, if we want to call it a solution, doesn't actually do anything. The problem that we've raised is the fact that matter and energy shouldn't exist. Not the fact that we need the sum of the matter and energy to be zero, the fact that it shouldn't exist at all. And in fact, ironically, Hawking has actually made their situation twice as bad as it was before. Because before, all that they simply had to do was come up with a way for matter and energy to pop into existence out of nothing. But now they literally need twice as much energy in the universe because they need the positive matter and energy, and they need an equal amount of negative energy. So they have to explain twice as much energy, and matter and energy interchangeably, to exist from nothing. I mean, it's an impossible event before, so you can't really say that it's twice as bad because 2 times infinity is still infinity, but it's, go with me here, it's literally twice as bad as it was before. Even more problems. If it happened once, why isn't it happening again? There's nothing, in theory, to stop it from happening again. So long as the total amount of matter and energy is the same, as long as you add x to both matter and gravity, the balance would be the same. So in theory, matter and energy should be popping in and out of existence all the time. Particles, rock clusters, infinitely complex galaxies should be coming in and out of existence all around us all the time. Does that happen? This is one of those not trick questions. No, it does not happen. And so because we don't see it happening, that indicates that this isn't actually how matter and energy work. And if it's not true now, if matter and energy just aren't popping into existence and popping out of existence now, that's not how it worked at the beginning. Okay? We are rocking through this.
Right.
Yep.
Just for the sake of the argument, you said yourself earlier that matter and energy deteriorate over time.
Right.
Could that be an argument as to why matter and energy is not popping in and out now?
Not necessarily, because it should still, like, if it happened once and the equation was in balance, it should happen again. Matter and energy are constantly deteriorating, and they're becoming less usable, but the same amounts of them exist. It's just in a less usable form. So the same amount is there. It's all still constant. It's just in a less usable form. But if all the matter and energy in our universe popped into existence at the beginning, whether or not that matter and energy deteriorates, it should still be happening now. We're actually getting significantly farther than I thought we would. This is a positive thing. Okay, we're going to move on to the singularity, which this is going to be fun. Why is this not working? My technology is frozen on me. There we go. Okay. Their claim is that the beginning point of matter and time was a singularity where the laws of physics just break down. How convenient, right? The laws of physics, they just don't work at the beginning, right? It just happens that way. This is theoretical physicist Ahmed Ali, and he said that the Big Bang singularity is the most serious problem of general relativity because the laws of physics appear to break down. They appear to break down because matter popped into existence out of nothing.
Oh wow, was he there?
I mean, I don't think so, because he's made of matter and energy, so he
Well,
probably couldn't be there when
he
there
said-
was no matter and energy, right?
He said appear, so he must have been there.
Looking back on it, it seems as if they break down, is what he's trying to say. This is physics author Amanda Gefter, and she says that the singularity is a place where the laws of physics break down. Whatever. This is this guy again, Stephen Hawking. He says that the beginning of real time would have been a singularity at which the laws of physics would have broken down. This is just silly, and apparently this explains away the issue that we have with the laws of thermodynamics, because of course the laws were broken, right? The beginning would have just been a singularity. Does this actually explain anything?
No.
And we're going to get in to the reasons why here in just a second. First, though, what do we mean by the term singularity? What do y'all think?
I'll start at one point.
It all started at one point. That's the general understanding of a singularity. It's not what they're using it to as.
An outline.
It's an outlier. That's a really good way of describing it. It's an outlier. And we're actually going to look at this because to help us understand what they're meaning by a singularity, we're going to talk about what mathematicians mean by a limit, because the two are very similar. And we're going to do this because I'm going to steal the screen from myself, and we're going to go here. And we're going to graph an equation. We're going to graph the equation y is equal to 1 over x. Okay? Y is equal to 1 over x. Let's just graph it. Let's just do it. Don't get too scared. You might want to get your calculators out. Imagine those are straight lines. Don't at me. Some of y'all might be getting a little bit concerned if you know what we're doing here about what's going to happen when we graph this point. Don't worry about it. We'll get there. We'll get there. Okay?
Your lines are straight.
My lines are not straight. I know. Give me a break on that. We're going to graph 1 divided by x. Somebody help me out. What's the value of y here if x is equal to 1? It's 1, because we're going to plug 1 into the x, and 1 divided by 1 it's 1. So let's call that 1. Fair warning, this is not going to be to scale very quickly. What happens if x is equal to 10?
Y is 5. No, 10, sorry.
Y is 10. So if we have 1 divided by 10, that equals 10. Get your calculators out. What is y here? Point 1. So like way down here. This is again not to scale. What happens at like x is equal a gazillion? Like tiny. So like let's zoom all the way in here. Let's get like there we go.
Not 0, but close to 0.
Not 0, close to 0. So we have a downward trend, right? We've got a downward trend here. Question: is this ever gonna get to 0?
No. It's not.
Is there any value that we can put in x? I don't care how far we go this way. Is there any value we can put into x where y is actually going to be 0? Your calculators might round it to 0. It will never actually be 0. Okay? Let's start going this way with it, though. What if x is like 0.5? It's 2. So let's go here. What if like 0.1? 10. So we're way up here. What it like whatever this tiny number over here was, let's do it like right here. What would y be? Huge, right? Skyrocketing. Imagine that was straight to it there. It's not squiggly. If we keep going, if we keep getting smaller and smaller and smaller, what do we think is going to happen when we actually hit 0? Maybe it'll be infinity. Right? As we get closer and closer to zero, we're going to get bigger and bigger. Infinity is not technically a number. But as we get closer and closer to zero, we're trending far more and more upward towards infinity. So maybe anything divided by zero is just positive infinity. Did we just solve math here? Because you can't divide by zero. If you try to divide by zero in your calculator, it's not going to work. Did we just solve math? No. And here's why. Let's start over here. Let's start graphing at like -1. Why is -1? What about it like, hey, let's do that point over here. What about it like -0.5? Why is -2? What about at -0.1? So we've got this trend here. So at zero, how can we equal both positive and negative infinity? It just breaks. Maybe we need a third dimension on this graph and it like wraps around the back of the TV to get to one the other. Like maybe that's how this works. We can't imagine 3D numbers. That's not how our human brains work. Stuff just starts to break. That's the points that I want to draw from a limit. Because what we've done here is taken a limit of 0. And point number 1 is that we're never actually going to get there. The limit might approach 0, y equals 0, as x gets huge. But we're never actually going to get there. There's no value that you can put into x for where y will actually equal 0. And as you start to approach a limit, stuff starts to break. Okay? Those are the 2 points that we're drawing from this. 2 observations here. You can never actually get there in a singularity. It's all theoretical. And even if you could, in theory, get there, stuff just starts to break. That's what they mean by a singularity. It's a hypothetical scenario where stuff just starts to break down. What you got? You got a comment?
I just wouldn't want to be resting my entire belief system on the possibility that everything just happened to break down. And it's just funny that creation is so out there and they have to break down all of their laws for it to be possible.
Mm-hmm.
That's it.
Well, and also when you think about outliers, like, they don't always happen once. So what you're saying, like...
Right. But there's, and that's actually a very good point, that they don't always happen once. I don't know if we actually get there. We might not, so we're going to cover it right now. They don't always just happen to once. There usually are outliers. And if it could happen to once, if it happened at all, why isn't it happening again? Do we actually observe the laws of physics just break? In normal everyday life? No. So why would we think that it happened the first time? There are numerous problems with this theory. First is that it's interesting to note why they believe it has to be a singularity. Because if you look back at those quotes, it has to be a singularity in their minds. It's not even a question. It just would have been a singularity. This just makes sense. If there was no singularity, and the laws of nature applied normally, stuff didn't just start to break, then matter wouldn't exist. But matter exists, as we've already looked at. So in order for them to make sense of their worldview, the beginning has to be a singularity. This is an indirect admission from them. They're saying, by definition, the Big Bang is an unnatural event. To get around that, they're forced to believe... I have 5 minutes left. We'll finish this section in 5 minutes. It's okay. They're forced to believe, regardless of the available evidence, that the beginning was a singularity. And they're forced to believe that such a singularity has to actually be possible, scientifically speaking. Again, here, everything is entirely speculation with no observation. One is scientific, the other is silly. By definition, like you said, because nobody was around to see the beginning, we can't actually know this. We can't know that the laws of physics just broke down. And so this is something that we have to be very careful about in scientific endeavors. In order to avoid outlandish conclusions from our speculation, we should only base our beliefs on what can actually be observed in our universe. Do we ever observe scientific laws just breaking down? No. So then why should we assume that it happened? That kind of speculation will lead us down really dark paths. Okay? We shouldn't go there. This guy again. What is really important is that these physical laws, as well as being unchangeable, are universal. They apply not just to the flight of a ball, but to the motion of a planet and to everything else in the entire universe. Unlike laws made by humans, the laws of nature cannot ever be broken. That's why they're so powerful, because the laws of nature are fixed.
Did he just say earlier that?
He did. He did. And we're going to get to that, actually, because the problems continue. Ironically enough, atheistic scientists actually do want the laws of nature to have applied at the beginning. They claim that they don't. That's too many. They claim that they don't whenever it suits their purpose. They claim that they want the laws of nature to have broken down when it suits their purpose, like to explain away the origin of matter. But in the very next breath, Hawking contradicts himself. This is that quote from earlier, where he said the beginning of real time would have been a singularity at which the laws of physics would have broken down. Nevertheless, it's not the full quote. Nevertheless, the way the universe began would have been determined by the laws of physics.
I didn't know Stephen Hawking really liked contradicting himself.
He wants his cake and eat it too. They're contradicting themselves. And they have to. They have to contradict themselves because that's the only thing that makes sense. Because the laws of nature show that matter shouldn't exist. And that the existence of matter is itself a supernatural event. So in order for them to hold to their atheistic worldview, they're going to have this internal struggle of trying to reconcile a supernatural event with an atheistic worldview. There's going to be contradiction.
It's almost like especially in time we'll figure out eventually with enough time and trial to explain this thing which is completely impossible to explain.
And that's, we're going to get there? I don't know if we'll actually get there. One of Darwin's funniest quotes, I don't know if it's a quote or if it's just something that he said, and I'll paraphrase, but he said that one of the greatest, after years of him sort of foolproofing the evolutionary timeline, he said that one of the greatest weaknesses at the end of his life, still in the evolutionary theory, was the fossil record and the lack of in-between creatures, the lack of intermediary creatures in the fossil record. And he just hoped that as science progressed, we would find more and more of them, and it would eventually prove his theory. So it's like you were saying, he's basing his entire theory on the hope that eventually it'll be discovered. We're going to get to it in like a month and a half. That's not yet happened.
It's kind of funny because they claim that it's like evidence-based, but they're in the face of the evidence against them. They're saying, "Oh, the evidence will fall in line with what I think."
Right.
You know, but they're claiming like, "Oh, this is all evidence-based." When in reality, they're like, "Oh, eventually, maybe evidence will back up my own biases," which is
Right.
like
It's evidence debt.
It's evidence
But
debt.
we'll
That's a
get
good
back
way
to
to put
it.
it.
It'll just take a while.
Yeah. And instead of just looking at the evidence that we have and following it to its logical conclusion, we have to, and that's a next week quote, we have to take the evidence that we have and bend our arguments around it in order to still make our worldview intact. It's them, not us. They're having to bend their arguments around available evidence to keep their worldview intact. The singularity does nothing to solve the atheist problem. All it does is indirectly admit that their worldview requires supernatural events in the first place. But because of their worldview, where supernatural events are not possible, they're still left with the same issue as before. Sneak peek for next week. We're going to talk about the multiverse.
Ooh, fun.
Spider-Man?
Yeah.